Welcome to Global Virtual School. Students, this is your first year chemistry class. I am Dr. Jalbanu. And the topic for today's discussion from chapter 3 is atomic hybridization of atomic orbitals with respect to sp2 and sp. Previously, students, we have discussed the hybridization with respect to sp3. Actually hybridization of atomic orbitals complete is with sp3, sp2 and sp, and in today's lecture we will discuss sp2 and sp, and after completing hybridization topic including sp3, sp2 and sp, you will be able to understand the tetravalency of carbon, trivalency of boron and divalency of beryllium. In our previous lesson we have discussed the tetravalency of the carbon, and I also told you about the how this concept was brought for the explanation of the some of the atoms that vary their valency. Partially filled atomic orbitals are related to the valence number. Valence number, if valence number is 1, it means that atom has 1 partially filled atomic orbitals, and if its valence number is 2, then it means it has the 2 partially filled atomic orbitals, and then it will form the 2 bonds to the other atoms. So according to that, beryllium is neutral, it has no partially filled atomic orbital. Boron is monovalent, it has only 1 atomic orbital, that is partially filled, and carbon is divalent because it has 2 partially filled atomic orbitals. But in most of its compounds, carbon is tetravalent. We have discussed in the previous lecture, and we will also discuss today that carbon has the tetravalency, it can form 4 bonds. And particularly today's lecture that regards to the sp2, we will discuss the trivalency of the boron, and in sp hybridization we will discuss the divalency of the beryllium atom, how the beryllium atom form 2 stable bonds to the other atoms. So first of all, sp2 hybridization, this is just like sp3. The difference is that it was mixing of 1s and 3p, and in sp2 it is the intermixing of 1s and 2p atomic orbitals to form 3 new hybrid orbitals, that is called sp2. p2 stands for sharing of 2p orbitals, and s1 only one s stands for sharing of only one s atomic orbital. So examples of bf3 and bh3, it can be cl3. First of all, I will write the electronic configuration of boron. Atomic number of boron is 5. So its electron configuration is 1s2, 2s2, 2px1. So 5 electrons are completed. This shows it has only 1 partially filled atomic orbital, and it should form 1 bond. But you can see in its compounds, boron form 3 bonds. So according to hybridization concept, there is excitation of 1 electron from 2s to 2py. In this way, it forms the 3 partially filled atomic orbitals, s of spherical, px of dumbbell shape, and py of also dumbbell shape, and all have 1 electron in them. So because pz do not participate, it has no electron, 1 or 2, it is empty, so there is no need to write it again. Now there is intermixing of this 1s and these 2p atomic orbitals to form 3 hybrid orbitals, that are sp2, and its shape is that it contains s character as well as p character, but they are not pure s, not pure p. So this is sp2, so this is also sp2. The larger lobe shows the participation towards the p orbital, and the smaller lobe show the participation towards the s orbital. And third one, sp2, this is sp2, and it also has 1 electron. So now we have this boron. So on this we will draw these sp2, sp2 and sp, so that they are at a maximum distance. So they will be at a maximum distance when they are distributed at a equilateral triangular shape, like this sp2, this is sp2, this is sp2, with 1 electron in it, with 1 electron, and with 1 electron. And so, and the other are its bonds are with fluorine, and there are 3 fluorine, like fluorine, fluorines atomic number is 9 and its electronic configuration is 1s2, 2s2, 2px, 2py and 2pz. 1, 2, 3, 2 to 4, 5, 6, 7, 8 and 9. So it has only one partially filled atomic orbital. It means it can form one fluorine will form bond with this. This is like Pz, and the second fluorine will form bond with this one, Pz of fluorine, and the one from and this Pz from the third fluorine, and they will pair up. Like boron will form with this fluorine bond and with this fluorine, and like this. As this bond is between sp2pz, and this bond is also between sp2pz, so total are 3 sp2pz sigma bonds. And in this case they have distributed, they have the maximum distance and minimum repulsion at an angle of 120. So angle is 120, and by this angle they have the shape of like triangular planar. So when you are asked to draw the shape of BF3 or BCl3, so you have to tell about the hybridization, is ground state, excited state, hybrid state, type of hybridization, that in this case is the sp2, then tell about the bonds, angles and the shape of the molecule. So in this way the trivalency of the boron is explained. So now come to the sp2 with reference to the ethene molecule, that has one pi bond and one sigma bond. You already know sigma bond is formed by the linear overlapping, while pi bond is formed by the parallel overlapping of the atomic orbital. So it means one of the atomic orbital of carbon will not participate in the hybridization, that will be drawn on parallel base, and they will form the parallel bond, that will be the pi bond. This is the ground state, excited state, and this is one S, this one is Px, Py and this is Pz. All have one electron in them, but in this 1s and 2p, these they intermix to form sp2 with this shape. One electron, sp2, this is also sp2, one electron, this is also sp2, one electron, and this is unhybrid Pz but with one electron. So draw this. This is the first carbon, this is the second carbon, and this carbon like it has two hydrogen bonds, and it has also two hydrogen bonds, and between carbon there is double bond. So one will be sigma, other will be pi, in this way. This is the carbon. Draw sp2 lobe on it. This is like this sp2, and like this one sp2. So sp2 one electron, it has one electron. So other carbon will also have like this carbon, like this sp2, and this one is like sp2 and sp2. So sp2 with one electron, with one electron, and with one electron, these are sp2. So there is one unhybrid, that is pz. Draw this like this one is pz. So same will be for other carbon, pz, as they have one electron in them. So first bond will be sp-sp. So one is sp-sp sigma bond, and with this there comes a hydrogen, and S of hydrogen, and also S from hydrogen, and also this S from hydrogen, and also this S from hydrogen. So these are sp2s. So sp2s, and total are sp2s bonds are 1, this one, 2, 3 and 4. So total are 4 sp2s sigma bonds. So total are 5 sigma bonds. Out of them, one is sp2 and 4 are sp2s. So as these are parallel to each other, so they parallelly overlap and form a pi bond. So there is one pi bond that is between Pz and Pz bond. So this is like carbon, this one and this one carbon, they have one sigma bond, one pi bond, one with hydrogen and one with other hydrogen, and this carbon also with hydrogen and this hydrogen, and these angles are 120, angle is 120, and this shape is like triangular planar, like triangular planar. So these are angles are 120. So this form a triangular planar shape. So what is the features of ethene? Is it has sp2 hybridization, it has these bonds, 180 angle and triangular planar is shape. So carbon basically when there is double bond, one is the sigma and the other is pi bond. So this is sigma and one is pi. So this is in this way the tetravalency of the ethene of a carbon in ethene is also explained with the help of sp2 hybridization.
In the ethene molecule, carbon forms bonds by using sp2 hybridization. sp2 hybrid orbitals are formed from 2s and 2p orbitals. This leaves 1p orbital unhybridized. The hybrid orbitals lie in one plane, directed towards the corners of an equilateral triangle. The remaining p orbital is perpendicular to this plane. Each of the four orbitals is occupied by a single electron. Head-to-head overlap of the sp2 orbitals of two carbon atoms gives rise to a carbon-carbon sigma bond. The remaining sp2 orbitals overlap with the four hydrogen 1s orbitals to form four sigma bonds. In this arrangement, the remaining unhybridized p orbitals of the carbon atoms are close and parallel to each other. They can overlap in a side-to-side manner to give the additional p bond between the carbon atoms. The carbon atoms in ethene are linked by a double bond composed of one sigma bond and one p bond. If we tried to rotate one CH2 group about the other along the axis of the carbon-carbon bond, one of the p orbitals would also rotate. As a result, the p orbitals of both carbon atoms would not remain parallel to each other. Rotation would require the breaking of the p bond. For this reason, rotation around the double bond is restricted and the ethene molecule is planar, with all bond angles close to 120 degrees. Notice that the sp2 hybridization concept explains not only the geometry around each carbon atom in ethene, but it predicts the planarity of the molecule too.
So now is the sp hybridization. So this is simple, like one s and one b intermix to form two hybrid atomic orbital, and this will explain the divalency of the beryllium. So example is beryllium chloride or beryllium fluoride. Atomic number of beryllium is 4 and its electronic configuration shows 1s2 to s2. So it has no partial field, it should not form the bond, but actually they form two stable bonds to the other atoms. One of the electron is excited from 2s to 2px in this way, because these are not participating in any bond formation, so there is no need to write here. And now there will be intermixing of 1s and 1px with one electron to form two hybrid orbitals, that will be sp and in this case also sp atomic orbitals. These will be sp and sp atomic orbitals. So like beryllium is this one, and shapes will be again same like sp3, sp2 and sp. This one lobe showing for p character, smaller lobe for s character, sp, because these are 1s and 1p, so there will be 50% s character, 50% p character. This is one electron, and the second sp, this is also have one electron, and on beryllium will these two lobes will be drawn like this, sp and in this way sp with 1 electron each. And now we have the chlorine, and you know chlorine's atomic number is 17 and it's 1s2, 2s2, 2p6, 3s2, 3px, 3py and 3pz. So 4 and 6, 10, 11, 12, 13, 14, 15, now 16 and 17. So it has only one partially filled atomic orbital, that is pz, and 1 electron. So pz of the chlorine, one chlorine will form a linear overlap. This is the pz from chlorine. So other chlorine will also form a linear overlap with sp of the beryllium, and they will form a sigma bond. Like this is beryllium with chlorine and this beryllium with chlorine. So this is the one sigma bond and this is second sigma bond, and these bonds are sp, sp, pz, total 2 sigma bonds, and they will be at an angle of 180. So there is maximum distance and minimum repulsion, and the shape will be of course linear. So what are the features of a beryllium chloride? That it is sp hybridization 1. It has 2 sigma bonds, that are sp, pz sigma bond. Angle is 180 and shape is linear. So sp will also explain the tetravalency in ethyne. In ethyne, students, you know carbon has triple bond with carbon and each carbon has 1 hydrogen. So there are total 3 sigma bonds, one carbon with hydrogen, other carbon with hydrogen, and between carbon, and the other will be pi bond. So pi bond is formed by parallel overlapping. It means 2 of the atomic orbitals will not participate in the hybridization, while the one will participate in the hybridization from p orbitals. So this intermixing, this is the intermixing of 1s and 1p. Other will be unhybridized, so they form sp and sp hybrid orbitals. So these are 2, while these will be unhybrid like this, but they have 1 electron, they will parallelly overlap. So consider this is the carbon, this is first carbon, so it has 1 sp, this is like 1 sp and other with 1 electron, sp with 1 electron. So and the second carbon, this one also will have sp and sp with 1 electron, and they are form bond with hydrogen, and you know hydrogen 1s1, and that is spherical shape, and one of the hydrogen will come here and will form a bond. This is s1s, and the other hydrogen will also form with this 1s, and one bond will be formed between sp and sp. Now where are these two? These two are unhybrid and they will be drawn as it is, like this is py. I am filling this with dots just to distinguish pz and py, and they also have 1 electron in each, and other one is pz. So this pz I am drawing like this, and this is filling with lines, and this one pc, and this also have 1 electron. So students, one bond will be sp-sp. So one bond is sp-sp sigma bond. Here this one, this is the sigma bond, and here is this the sp-s sigma bond, one, and one also sp-s sigma bond, second. So two are sp-s sigma bonds, and now there will be parallel overlapping between py and py, because py and py they have the same symmetry. So there will be this pi bond, one pi bond between py and py, and pz and p is also parallel to each other, and both have the single electron partially filled, so they will form the bond in this way, a second pi bond, and one pi bond is between pz ez pi bond. So students, basically this is carbon and carbon. This one is the sigma bond, this is with this hydrogen sigma bond, and these are due to py and pz, these are pi bond, these are sigma and these two are pi bonds, and the angle will be like 180, and this shape is linear. So there is sp hybridization in ethyne. Hybridization of carbon is sp in ethyne. Bonds are total 1, 2, 3, 4 and 5. Bonds are 5. Out of 5, one is sp sigma bond, 2 are sps sigma bonds, and one is py pi bond, and other pi bond is between pz and pz, and angle is 180 and shape is linear. So when you are asked to draw the shape of ethyne, you have to explain with the reference to the hybridization, type of hybridization, their bonds, their geometry, draw their geometry, and what is their shape and their angles. The next animation will explain you little more about the ethyne.
The ethene molecule contains a triple carbon-carbon bond in which both carbon atoms are sp hybridized. The hybridization of one 2s orbital and one 2p orbital produces two sp hybrid orbitals with two free, unhybridized 2p orbitals. One sp hybrid orbital overlaps head-to-head with the similar sp orbital of the second carbon atom, thus forming a sigma bond. Two other sigma bonds are formed because of the other sp orbital of each atom overlapping the 1s orbital of a hydrogen atom. Unhybridized p orbitals are perpendicular to each other and to the axis of the sp orbitals. These unhybridized orbitals can overlap side to side to form two pi bonds with a cylindrically shaped electron cloud around the axis of the atoms. The triple bond in ethene consists of one sigma bond and two pi bonds. The ethene molecule has a linear shape.
So this was all about the sp2, sp3, sp hybridization. So now let me compare the ethene and ethyne. So first of all, ethane, you know, in ethane carbon has single bond, and each carbon has 4 bonds, 3 with hydrogen and 1 with carbon. So this is the ethane. In ethene, double bond between carbon and 2 bonds with hydrogen from each carbon. And in ethyne, there is a triple bond between carbon, and each carbon has bond with hydrogen. Its shape is tetrahedron, and its hybridization is sp3, while ethene has shape triangular planar, and it has sp2 hybridization, while ethyne has linear shape and it has sp hybridization, and angle will be in ethene 109.5, and in ethene it is 120, and in ethyne it is 180 degree. And the total bonds in ethene are 1, 2, 3, 4, 5, 6, 7 sigma bonds, and out of them one is sp3 sigma bond, and 6 are sp3s sigma bonds. And in ethene there are total 1 pi bond and 5 sigma bonds. One sigma bond is between sp2 sigma bond, and 4 are sp2s sigma bonds, and one is pi bond between PZ and PZ pi bond. While in ethyne there are 2 pi bond and 3 sigma bond. Out of them, one is sp sigma bond and 2 are sps sigma bonds, and one is py pi bond, and one is like pc and pz pi bond. So students, this is the comparison and explain the how the hybridization explain the tetravalency of the carbon, and in previous discussion trivalency of boron and divalency of the beryllium. So this was usually question asked in exams are about to draw the shapes of like methane, ethane, ethene and ethyne on the base of hybridization. Hopefully this will be clear for you. So this was all about the hybridization in today's sp2 and sp, and previously we discussed the sp3. Students, our next topic will be molecular orbital theory.